Hi friends, so today we are on a new subject. It is called Prognostics and Health Management, a systems approach. Probably you would not have heard about this subject. This is a new strategy for maintenance management and operations of complex engineering system. And health prognostics and health management is possible now. It is the central element is AI and ML. That means artificial intelligence, machine learning, and of course deep down we have a deep learning strategy also here. So with that only prognostics was possible. All of you must have heard about diagnostics, but prognostics is a thing which has been derived from prognosis. That means predicting something a priori. And the objective of this whole discussion or presentation will be how we can eliminate, if possible, or reduce failures in the system in such a manner that our reliability and safety are not compromised. Because today's systems, they are very complicated, and one term can define them as a complex, whether it is human factor interaction or whether it is a interdependency among the component and processes, and of course digital system now slowly it is becoming, or rather except for certain safety critical system like nuclear plants, digital technology is becoming part of, and there we have the software element sitting there. And the biggest challenge is we have to take care of a factor called common cause failure. Common cause failure is very important. Why? Because it kills the built-in redundancy and at times even the diversity also because of external elements. So prognostics and health management, even though it is a new field, but it is slowly getting incorporated into the operation and maintenance, especially for some areas like aviations, and even dams also prognostics is done. Sensors are put to continually get the information about degradation of the structures and systems. Today is first week we are starting. So lecture and week there. So each week has got 5 lectures, and that's how the course is built. So total in this course there will be 60 lectures. Okay, so I'll introduce myself. I am Professor Prabhakar V. Vardhe, CEO and Director of ERMC, is acronym for Engineering Risk Assessment and Management Center, India. And of course, I was Associate Director, Reactor Group, Senior Professor, Homi Bhabha National Institute and Bhabha Atomic Research Center. And currently, I am also Guest Professor, Department of Operation Maintenance, Luleå Technology University, Sweden. So with this brief introduction, we start the lecture, and first I'll give you the background. Why the PHM technology is required. Though there are 2 major focused areas in PHM, one is electronics and reliability. Quite a bit of work has been done at international level, and then we have these mechanical components like pipe, valves, pumps, motors, and there also the major output of PHM is remaining useful life. So a lot of work is going on to have to track the degradation and try to assess the remaining useful life. And particularly for complex engineering system, there are challenges, because PHM in first glance it is a component based approach. But then if we have a system wherein n number of components they interact with each other, and finally the system gets into the operation mode, and delivers the product or services, whatever it is. And then safety should not be compromised. So as I mentioned, the redundancy, diversity, their integrity should be maintained, and of course there should not be any failure which lead to common cause failure. I'll come to that point. So the objective is to meet the in operation and maintenance safety and reliability targets. Of course, risk cannot be zero with any system, any entity. Risk component is there, but it should be in the acceptable range. So that addresses our safety issues, and then reliability issues. Our deliverables, like if for a nuclear power plant, electricity generation should be highly reliable, so that there is no interruption in the public domain. And even for facilities like hospitals and all that, even though big facilities, they have their own captive power, but then the redundancy is killed. Like if we have a normal grid power failure, then we have to depend on, so margin is reduced. So that situation can be avoided to the extent possible. And then if you want to give me, if you want me to give a gist or what we are trying to achieve, so that means failure management. Either it should not be, failure should not be there. If they are there, we should be able to manage it. That's why prognostics, first you try to predict whether the incipient failure is there, and if it is there, then what is the remaining useful life. Because the remaining useful life predicted by PHM, that is Prognostics and Health Management, it enables us to to make the arrangement so that the consequences of failure can be managed or eliminated altogether. So, and then this is part of a maintenance approach. PHM is an advanced technology for maintenance. I'll see how this technology has evolved in the subsequent slides. And then the enabling technology for PHM is AI/ML, artificial intelligence and machine learning. I am using all through some abbreviations, so please get used to it. AI/ML stands for artificial intelligence and machine learning. DL for deep learning. Okay, and as and when these acronyms come, I'll keep on spelling giving it. And then what we said, higher level objective is minimum acceptable level of risk. Minimum acceptable level of risk for any complex entity it be. And reliability assurance, that means plant should have failure free operation to the extent possible, and all these targets in a company are built when these companies are launched. If they are not, people try to give targets actually, you know. So though the PHM is an enabler for allowing us to predict the remaining useful life of a component, and that in turn avoid the consequences of failure. But then there are some challenges when we talk about PHM technology. And so if you look at the status and publication, you will find that in quite a few sector it has been being implemented in a phased manner, but otherwise it is an intense subject in laboratories, and a lot of research is going on to meet these challenges. Okay. So one is complex system. So that means PHM in that sense it is a components approach. But then there are many components in the system, and that make the system operable. Okay. So which component should be stressed for PHM, because PHM is a resource intensive technology, and of course R&D wise also a lot of R&D has to be done. So all the components cannot be subjected to PHM. So there has to be identification and prioritization. So before that, we should have a systems approach to PHM, and that's all this lecture is all about. Because PHM examples you will find, but given that one or two examples of their failure mode effect analysis to operate PHM on system level, this lecture will provide a broader and rational based strategy, and that is and that can deal with the complex engineering system also. So here we will be introducing a subject called probabilistic risk assessment, and thereupon we have risk-based engineering and risk-conscious operation management to handle the systems problem. Okay, the technology has come up to, maintenance technology has come up to condition-based maintenance approach. But condition-based maintenance approach, if you visit a factory, advanced factory, you will find it is not there for all the components. It is there for only few selected components. And even the condition-based maintenance provides the information about degradation. Now, we do not know when this component is going to fail. So, this is what that additional input comes from prognostics and health management. And the PHM has provision to predict the remaining useful life, number one, and number two, provide with uncertainty. Okay. So, this is that's how it becomes very attractive proposition for consideration into the industry in general and complex systems in particular. And now if you look at the causes of the failure, there are human error, institutional aspects, like failure do not always happen. If you perform the root cause analysis, you will find, okay, the failures appears to be due to human error, but sometimes there are institutional aspects like procedural inadequacy, training, technological, complexity of plant design, and the time window that is available for taking action. So these are the factors that and especially in emergency condition, the chances of failure is more because during higher stress level, the chances that a person or a human will commit mistake is more compared to the normal scenario. And sometimes the problems come because of material, tools, quality and issues. So why I am talking about human, even when we are talking about prognostics and health management for hardware system, why can't we talk about the human prognostics? We should be able to detect in advance, and this is something at least I have not seen any publication. So I'll introduce this topic, why human prognostics cannot be done. Why even software prognostics cannot be done, but okay, so this kind of, and that will be useful, software prognostics, it will be useful for those software do not age, but there are some certain factors based on which if we see some symptoms, we can remove the failure. It is in software domain, software reliability domain. Okay. Now the advances in maintenance management approaches that provide superior model of, so this is the sort of a conclusion, but again there is always a question on prognostics and health management. As I said, it is a resource consuming option, so return on investment. Lot of studies are there where return on investment. So this factor will go because any company who is trying to shift from the CBM or from other maintenance approaches to PHM, if not in totality, even if a part of the system like for safety system gets priority, and then safety support system gets priority, and then process and operation system they come into picture. But return on investment is very important, and so that catastrophic situation or catastrophic failure are avoided. So now let us see the advantage. There are many advantages. I have failures are expensive, particularly common cause failure. So a new aspect while drafting this, preparing this presentation has come out, which is common cause failure. Before we work on PHM of individual component, we have to talk about, because if you see in risk analysis, if you see the common cause failures has been found and that too induced by human factor. So these two together, they occupy a bigger dimension in safety analysis. So how to handle this common cause failure and human factor and all that. So I think if we can think about it, even though we have provision for to avoid common cause failure like barriers, separation, power supply, independent power supply and all those we do. So that means we have some idea about, we have a good idea about how common cause failure occurs. So that means we go to the event which is causing common cause failure. And if we start from there, probably for safety and reliability, it will be a big favor. So in my knowledge view, the PHM should start from common cause causing factors or events. So this is the point here. And then PHM appears promising towards eliminating or reducing failures. Why? Because it can predict in condition-based maintenance, we were predicting the degradation, where the degradation starts, and then here with data and models and methods and physics, we can provide estimates of the remaining useful life. And of course, it cannot be point estimate. So always uncertainty prediction. So uncertainty prediction forms part of PHM, remaining useful life prediction, and that's how we'll know the upper bound, lower bound, and mean or median value. And it is a complete estimate. So that is possible. And then the third point is predicting RUL helps in improving reliability while lowering risk during plant operation and maintenance management. It is a promising approach. Yes, it can reduce the failures, and it offers unlike our condition-based maintenance approach, it offers it interacts. The failures have context when it has failed, and whether we have plant data, whether plant is shut down annually or it is shut down monthly, or so we can plan the maintenance program. If it is a severe warning, then immediately plant has to be shut down. If we can wait for some more time and see the trend, whether it is increasing or getting stabilized, then we can go on operating, go to the next shutdown. Or if we feel okay, let us. In plant many discussions occur. So certain other events are also waiting. So let us club it into it and take a small shutdown. So the most important part of PHM is management actions can be initiated, and that without causing any consequences to the extent possible, and then we are having a failure-free operation. So you can see failures, we think it is an integral part of any system, but you can avoid it when you monitor the trends of degradation, and thereby you have an estimate of remaining useful life. And then we have this in operations. It is basically, it can schedule the operations if we have some issues, and in maintenance PHM can be very useful in terms of losing because if you look at the traditional approaches, therein a lot of useful life is lost, because we are shutting down the plant. If mean time to failure or mean time between failure is, let us say, X, then remaining more than 30% to 50% life is remaining, that goes waste. So here you are shutting down when degradation, we are approaching almost the failure. So lot of useful life, so maintenance activities will be reduced, and then that will reflect on requirement of manpower, spare parts and all that. So overall, I think if we have good experience, it will be a good return for the plant also in terms of financial component. So these are the advantages. Then major approaches. I'll not provide details. That will be somewhere when we talk this particular subject independently, like various maintenance approaches and all that. But here I'll say the evolution of maintenance has occurred. Initially, it was a breakdown maintenance. Keep operating the component till it breaks down. But then it affects the plant as a whole. So preventive approaches have there, and one of them is preventive maintenance. That is, it is periodically maintenance are carried out, and it is something like a qualitative input that which component fail more, which component fail less, and all that. So accordingly, it comes to whether it should be monthly preventive maintenance, whether it should be annually. Like for passive system pipes and all that, it is 4 years they are inspected, okay, and that is called in-service inspection. And then there also there was some excessive maintenance inspection was being done. So risk-based or risk-informed maintenance, these things are there. And of course, where there is a throughput and there is a risk component is very low, even reliability centered maintenance also does well actually. And as I said, the most advanced as of now that available is condition based maintenance approach, wherein you monitor the precursor. Precursor means a parameter which will be responsible for the failure. Okay, and then degradation level, some limits are maintained, and if the degradation level reaches there, then the activity start in terms of maintenance management and prognostic health management. It provides the remaining useful life along with the uncertainty, so that further now we are pretty sure that compared to condition based maintenance, that what kind of activities have to be implemented in the plant to avoid the consequences of failure. So you can see here, maintenance management is critical to ensuring higher plant reliability, reducing interruption. Reliability means reducing interruption and operating the plant at full capacity, and then availability and improve safety by reducing the failures. Well, just to give you idea of what are the complex system, here is an example of nuclear plant, and then a complex bridge structure. Okay, so nuclear plant here, then it is a bridge structure, then it is a railways. All these are advanced technologies, as you can see here, and that's why the demand or the expected service is so they can be called as demand oriented system, and then we have aviation, then we have this space system. So you can see in all these systems, and of course the offshore technology, and then maritime things. So these systems can be put in the category of complex system, because whether it is human resource and human intensive activities are concerned, or whether it is a failure that you need to avoid at any cost, or any redundancy should not get compromised, and sometimes the management activity, if they are efficient, like if it is replacing a module, it can be done within no time. But if it has to be assembled, and which is a time intensive activity, then probably we compromise on that. So these are some examples, just to give an idea to my viewers. These are the complex systems, and that unless until there are optics available, we don't understand what it causes a particular accident. And if it has gone into our conscience, that what is that scenario, accident scenario, so the consequences are, it could be fatalities, loss of property, loss of reputation, financial impacts, loss of production, might lead to larger unrest, changes in perception on safety, social impact, healthcare, forensic, might have national and international, international exposure also. So consequences also. So just to get an idea, in 2023, this Balasore accident, railway accident happened. Almost 296 people died and 1,200, and probably it is left to the imagination that there is nothing more important than safety and mitigation of accident in timely manner. If at all they happen, it should not happen, but if at all they happen, so this is what we have. And then let us take the aviation sector also, because we are talking about safety and reliability, so it should go into our conscious mind what is acceptable risk and what is not acceptable risk. Okay, so you can see on 12 June 2025, AI 171 Boeing 787, it in Ahmedabad, it crashed. 241 plus 19, this figure might be, it changes here and there. So 10 people died on ground, it seems, and this one, and then direct cause was plant, that fuel supply was available or not. Full report has not come, and then you have 13 accidents. So in how many years? 67 years or 63 years, if I'm not wrong. So this can be said that we should be, of course, prepared for improving safety and all that, and it should not be compromised. Safety should be overriding factor and all that. But sometimes a lot of useful activities are happening during the travel. So we should be. So as I said, 63 years, 13 accidents happen, and then if you see the failure rate, I mean, it is just an idea. This may not be exact data. So 0.2 per year, and then assume somebody was catching a flight, and then suppose in a year, if I assume that 3,000 flights are there in India, this study is about India specific, so in a year, almost like so many flights, like 11 lakh flights were taking off and landing actually. And then this implies that the probability of the accident is 1.2 into 10 to the power minus 5. Okay, so it is going almost in the range of 10 to the power minus 6. So we can say it should not happen, it should be below this only. But then, as I said, a lot of useful activities are done, and with even we are traveling in an elevator, and then there is a chance of fatal accident, maybe low. So, according to me, this risk, that if I am taking a flight, if somebody tells me your flight is going to meet an accident and the probability is 10 to the power minus 5, I'll say it is almost getting theoretical, if not hypothetical. Okay, and then mission is our takeoff and landing. So this is the probability that your flight, and this is something, and that is subconsciously there in the people's mind. Okay, the accident happened, but there are many important things to be done, and that's why the aviation business goes on actually. There is a special interest in railway and aviation sector for PHM implementation. In fact, first few implementation, if at all, anyway, they are generally for electronics, and then next it will be aviation, space, and PHM. So this is the sort of I would not say popularity, but eagerness to adopt these kind of systems. Now, role of artificial intelligence and machine learning. One word is sufficient at this stage. AI, ML, they play a central role in prognostics and health management. And this topic will come all through the 12 weeks in some way or the other way. Okay, why AI, ML should come? Because you are in the domain of non-linear. In mathematics we call linear and non-linear. It's a non-linear problem, so AI, ML is required, because sometimes it is selection of pattern, sometimes it is selection of the trend. So, and that will give you a prediction, and then degradation data if you want. That also physics of failure can help you in this. And again, with the AML we can do. Otherwise, even database approach. We are using two approaches here: database approach or the physics of failure approach in PHM. So both are required, but nowadays the database approach is gaining popularity, because understanding the physics of failure is a very complicated task. But then if we combine these two approaches, then I'll be discussing this part also in the next slides. Future slide, not next slide, I would say. So we will be discussing each of these threadbare actually. So when you combine data-driven approach and physics of failure approach, what we are doing is basically we are reducing the uncertainty, because there was some prediction was there, and then other prediction comes and then it tries to correct it, and that's in that the chances are there that uncertainty reduces. So other than the artificial intelligence, there are a lot of statistical approaches are also used for coming to the inference that what should be the remaining useful life. There are some references, probably you can access them, okay, and and there is a PHM society which has developed a standard, there is a journal and there is a standard also. You can see a IEEE standard developed through PHM society, and then I have some papers and all that. This you can probably you can access these papers in public domain, and yeah. So here we finish our introductory lecture on prognostics and health management systems approach. The complete title is Prognostics and Health Management Systems Approach. System approach is a contribution of this particular course.